Well, good evening, everybody. Welcome to Ellensburg, Washington. How y'all doing tonight? Good. We doing okay? Audio, visual. Yes, obviously trying something new tonight. We have very strong winds this afternoon. My chalkboard went crash, and I figured that was a sign. So I'm in the front porch, and we'll see how things go with the lighting here. But yes, now that I'm kind of looking at your comments here, are we doing okay with audio, the stream quality, the video, even though the lighting is, yeah, I don't like the lighting. Good? Yes, thank you. Oh, sure, yeah, I've got, it is a little dark, I agree. I'm debating about doing something here. Sun's not going to be coming through that window for another 15 minutes. Let's try a couple things. So that looks pretty good, doesn't it? I mean, we can, for things I'm holding up, this might even be better than what we had outside. Yes, good. Yeah, I mean, you know what I look like. You don't need me super illuminated. Let's try a couple whiteboards quick. This is from Sunday morning. Yeah, this lighting is good for this sort of thing, isn't it? I mean, I can really come in and, yeah, okay. Well, that's good to know. So I can share with you my setup here. I've got two lamps from the living room that I dragged out here to the front porch. I had to clear out this part of the front porch. I've got, except for this window where all the high wind is coming through, I've got everything else open, including the front door propped open, because I wanted to minimize the echo. I think that might actually be working. I don't think it's quite as echoey as it was before. Oh man, these lights though. This is like orange. I don't know if I like that. Oh, my mom is here? Oh, good. Hello, Mom. So here's our schedule for the rest of the week. Tonight we're talking about plate tectonics, kind of a part two to what we were doing before. You're welcome to come back tomorrow night where we'll talk about something called the Straight Creek Fault. I'll give you more info on that in a second once we get started. Oh, I forgot to even tell you. Sorry. I knew I was forgetting something. So it's 5:51 p.m. We're going to start our program at 6 o'clock. 9 minutes to go before we start. This episode brought to you by Timex. 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 You got to love it. So Thursday, Hell's Canyon. Saturday and Sunday mornings, age dating lectures. Okay. I like everything except the lighting so far, and this will be our experiment tonight, and we'll see if things improve once the sun kind of lowers enough to kind of flood into this room. And if it's still this kind of artificial yellowy light, then we'll figure something else because it's supposed to be wet tomorrow, so I'm probably going to be in the front porch again tomorrow. Okay, a couple of quick thank yous. Got a nice card and some chocolate chip cookies, a lot of chocolate chip cookies dropped off at the house yesterday. Thank you to Cheryl and Don for doing that. Very kind of you. Some homemade dark chocolate. You can see the theme here. From Marty and Dale. They dropped by and dropped that off on the side porch. Thank you to you guys. This arrived. This is a test for you. This arrived in the mail from Rick in New Mexico. Handcrafted on a lathe, I assume, Rick. And what is this? That's your test. And I'm giving you the test because I thought about it for 4 days. Still couldn't figure it out. So there's this. It's kind of real heavy. And then there's this beautiful shape. And then I'm like, oh, this opens up. Oh. So I can like put secret things in there. So I think it was this morning. Was it this morning or yesterday? I finally emailed Rick and I said, Rick, I've been thinking about this and I'd like to thank you, but I can't figure out what this is. And so he sent me a photo of how to use this. And I haven't seen all your answers, but probably somebody's probably right. So let me go get something from the kitchen and then I'll show you what this is. A lot of pepper grinder, a lot of weed. I don't know what you're talking about with that. This episode of Nick from Home brought to you by Irish Death beer from the Iron Horse Brewery in downtown Ellensburg, Washington. You gotta love it. Thank you, Rick. I love it. It's a bottle opener. Hello. It's a bottle opener from Rick in Silver City, New Mexico. I think that's your town. Thank you so much. I'll be back. We will begin our program on plates colliding, tectonic plates colliding to make different kinds of mountain ranges in 3 minutes, I guess. We got 460 people. That's nice to see. Where are y'all from? I assume this is mostly a North American audience since we're back on our muffler boy. Vancouver Island, Iowa, Mike, nice to see you. New Hampshire, California, Maine, Prescott, Arizona, Columbus, Maryland, New Jersey, wonderful. Vancouver Island, hello. Tri-Cities. North America, says John. John must be on the lam. Hermiston, Mound, Minnesota. A few of you in Japan, that's nice. Garrett from the Netherlands. Must be 3 in the morning there. Winnipeg. Welcome, especially to those of you that are new to us. Welcome. It's official, I hate the lighting. We'll make it work. I got 2 minutes, damn it. I'm turning you around. I'm going to turn the whole ladder around. That's better, isn't it? Isn't that better lighting? Good, that's what we're doing. Give me an extra 30 seconds, would you? Yep. I like this better. Oh, that didn't screw up the audio or anything, did it? I feel like the lighting is more natural this way, and especially we're going to lose more, the sun is going to get more and more in here in the next half an hour or so. Okay, good. I got 6 o'clock. Well, a pleasant good evening to you all. Welcome to Ellensburg, Washington, especially those that are new to us. Tonight we're talking about more plate tectonics. For those of you that were with us on Sunday morning, the last time that we did a live stream, we were focused on the oceans of the world and talking about seafloor spreading and some exciting discoveries back in the 1950s and the 1960s to make a transition from continental drift, which was a controversial idea that was not accepted really by most scientists. And then by the end of the 1960s and into the mid-1970s, for sure, plate tectonics was fully embraced by everybody and continues to be embraced to this day. There are still some fundamental questions left. We'll probably touch on a few of those questions tonight. But for the most part, I want to leave the oceans and go to the continents and talk about different kinds of mountains for the most part. And there'll even be more involving plate tectonic basics tomorrow night. We're going to go to a place called the Straight Creek Fault, which I doubt even Washingtonians, people that live here in the state, know much about. It's unknown because it's dead. It's not a threat anymore. But when the Straight Creek Fault, tomorrow's topic, was active, it was a major structure. Oh Lord, I see an animal. Hey man, you want to join us here? Okay. That's Bijou the cat. So, I think I'd like to start. I'm particularly loose tonight because I've talked about plate boundaries for a long, long time. So I feel confident that we can do a fair amount in a reasonable time. And in a half an hour or so, we'll turn it over to you and we'll take this wherever you like, question and answer wise. This is live. I'm talking to you in real time. Let's start with one of our images from last time. So this is a plate tectonic cross-section going from San Francisco, California to New York City to Lisbon, Portugal, and I suppose it goes over to Tokyo, Japan even. And the purpose of this is from last time. I'm not going to spend an hour on this. We're just going to do it very quickly. I'm reminding you that we now know the difference between continents and plates. I didn't say it this way last time, but I can say it now. Continents are just portions of plates that are above sea level. That's really the way to think about this. We live on the 7 continents, but those continents are portions of much larger slabs of the Earth's lithosphere called tectonic plates. And our focus last time was on the Mid-Atlantic Ridge and this activity where the 2 plates here, the North American plate and the Eurasian plate, are splitting away from each other, and flowable, warm asthenosphere comes to the surface and it gets shallow enough to create lava, and we're actually creating new ocean crust. That was our story last time. We talked about the Atlantic Ocean getting wider and wider. And so, this is going to move on its own, so I'm not going to be able to pin it down like I want. But it is accurate then to say, based on the fact that we know that the Atlantic Ocean, there it goes, the Atlantic Ocean is getting wider and wider every year, and the Atlantic Ocean has been getting wider and wider every year for the last 200 million years. That does mean, can I get you to the Pacific here? See, it's, I can't. This is such a tempting prop that you could think you could do all sorts of things with it, but you can't even, anyway. It's the Pacific that's getting smaller and smaller. So we are not getting bigger and bigger as a planet. Tonight we're talking about destroying ocean crust, primarily in the Pacific Ocean. And you know that I'm in tune with what large numbers of people always want to talk about. I think I've said this a number of times. There are certain phrases or concepts that just bubble up, even in a casual conversation in the produce section of a grocery store. When we go, oh yeah, geology guy, oh yeah. So one thing that comes up is Ring of Fire. Everybody wants to talk about the Ring of Fire, not just the Johnny Cash song, but Ring of Fire. They know about the rim of the Pacific Ocean having lots of volcanoes. We'll talk about that tonight. People also always want to talk about the Mariana Trench, or the Marianas Trench. People say it differently. And the fact that this part of the ocean floor is dropping out of sight is captivating to many, and exploring that deep, dark hole. So we'll comment on that as well. I do have a structure, even though I'm loose tonight, I do have a structure. Because what's the title? Tectonic plates colliding. So we're going to focus mostly on that. But let's find the other whiteboard. Bijou has left the front porch and he's out playing now. The only negative of going this way with the ladder is I've got a glare now, but you can handle that, right? So, what we were just talking about with the Mid-Atlantic Ridge or the East Pacific Rise is a divergent plate boundary. A divergent plate boundary means the plates are moving in opposite directions. I'll get back to that whiteboard in a second. So you remember, last time we used my Geology 101 textbook from Madison, Wisconsin that cost me $20. And here's Marie Tharp's spectacular image of our planet with all the ocean water sucked out of the ocean basins. And yes, I'm talking about the Mid-Atlantic Ridge being a divergent plate boundary, and the East Pacific Rise in the Pacific Ocean as a divergent plate boundary. And you might immediately be going, well, wait a minute, hold it. Didn't you just say with that dopey globe that didn't really help me, I didn't see it, didn't you just say that the Atlantic is widening and the Pacific is shrinking? And I'm saying, yes, that's true. We have GPS instruments on all the continents now, and we know that's for sure thing. The Atlantic is getting wider, the Pacific is getting smaller. We're narrowing the Pacific. We're destroying Pacific Ocean crust. We're not destroying Atlantic Ocean crust. And then you might go, hold on, isn't this a seafloor spreading center? Isn't this a place that you're making ocean crust just like here? And the answer is yes. You can see I've taught this a while. I can almost anticipate the questions that usually come up. So then a hand goes up and says, well, why? Shouldn't there be like a stalemate? Like, aren't you making crust here and making crust here? And why is the Atlantic essentially winning and the Pacific is losing? And the quick answer to start, although it's not going to make total sense until we get into the whiteboard, the short answer is these continents are connected to this spreading and not this spreading. And we'll see in just a second that you can have ocean crust that's even moving faster than the continents, but it's the ocean crust that's going to get destroyed. It's going to lose. So it's almost like this is an offensive line or something, and we're doing all this blocking out in front and protecting that precious crust in the Atlantic Ocean basin. And it is true that the East Pacific Rise, we mentioned this last time, the East Pacific Rise is spreading faster than the Mid-Atlantic Ridge, but it's losing. And these continents are getting closer and closer to that East Pacific Rise as time goes on. Okay, I want to do one more thing before we go back to the whiteboard. A statement I actually meant to make last time and I didn't get to it. So this is almost like housekeeping for me here. I'm sorry, Mom, you told me not to drink beer, but I'm doing it. Ooh. So I have a little course pack that I use for my Geology of Washington class. It's taught at a very low level. My gimmick is, with these classes at the 100 level, I have a bunch of freshmen who don't have any interest in science, and geology sounded easier than chemistry, so they just show up. They're not even sure what it is because we don't teach geology in this country hardly at all in K through 12 classes. And so it's easy for me to excite people because they haven't heard most of this stuff before. But I especially like to teach it this way. I say, well, yeah, we're going to learn some Geology 101 content, but this is Geology 103. We're going to take the 101 content and apply it. We're going to keep applying it to our state. We're going to apply it to places that young 19-year-old who grew up in Federal Way, Washington, or Snohomish, or Moses Lake. We're going to try to plug this stuff in right to your backyard as opposed to a distant place. So I have all these kind of hand-drawn things that students have this with them every day, and they take notes on them. It costs them less than $10. I'm proud of that they're not paying hundreds of dollars for course materials. But this is a map that I drew long ago that I use every quarter, and I want to mark it up for you. What are you looking at? You're looking at familiar continents, but you're also looking at these black lines, which are plate boundaries. And until we learned about plate tectonics in the 1960s, can I do this without looking? I'm kind of looking backwards into my phone, but I'll try it. No, I can't do it. So in the centuries before the 1960s, centuries now, not decades, in the centuries before the 1960s, it was clear to people who had been traveling the world that the red dots are volcanoes. This is not even worth my time, by the way. I'm going to stop. Not even going to worth it. Almost all volcanoes and almost all earthquakes happen at plate boundaries. There's exceptions, but almost all earthquakes and almost all volcanoes happen at plate boundaries. And that was one of the most basic observations by scientists for hundreds of years. Why do we keep having all these earthquakes and volcanoes on the west coast of North America, but not on the east coast? Yes, I know there's exceptions, but in general, why do we have all the earthquakes and volcanoes on the west coast of South America, but not the east coast, etc., etc.? What's special about these certain places on the planet where we have all these earthquakes and volcanoes? We now know the answer. We've known it for 50 years. Almost all earthquakes and almost all volcanoes happen at plate edges, at plate boundaries. And so that is what this whiteboard is about. We are simply looking at different plate boundaries and looking at geologic phenomena that happen. What's happening at divergent plate boundaries? Like the Mid-Atlantic Ridge or the East Pacific Rise, the plates are splitting away from each other. Do we get earthquakes? Actually, we do. We have earthquakes at all types of plate boundaries. Do we have volcanoes? Of course we do. Of course we do. Iceland is full of volcanoes. Our topic is in red. Let's skip over it for a second, but basically convergent plate boundaries are just like you see here, where the plates are actually colliding together. And then at the bottom, I'm going to save that for tomorrow, because the Straight Creek Fault, the topic of tomorrow night's topic, the topic of tomorrow night's session, the Straight Creek Fault and the San Andreas Fault are transform plate boundaries, where the two plates are actually sliding in a horizontal sense and not colliding. Okay? So for the rest of tonight, we're doing this. We're bringing two tectonic plates together and we're colliding them. And you can see that is a common occurrence on a world map. There are plenty of places where we have these big fat black arrows that are actually coming at each other and colliding. And if you're brand new to plate tectonics, maybe you're a young person watching us, or maybe you're a person who took a science class in the 1950s and never did hear about this plate tectonic thing, or maybe you just need kind of a little polishing on your plate tectonic knowledge. We're going to travel around the globe in the next 20 minutes and visit different mountain ranges and talk about what type of a convergent plate boundary it is. So now that you know that plate boundaries are important, you probably did already. Here's another way to look at the same thing. I'll come in pretty tight, but you've got glare now. Maybe you can deal with it. So you can see these black lines are very specific, and we have names for each of these tectonic plates. But the black lines are not equal. That's my point. In fact, on this map, they're actually making the divergent plate boundaries red to show you that magma is coming up along the plate boundary. It's a whole new way to look at our planet. And now that we're sure by measurements that these tectonic plates are moving, we know the direction they're moving, we even know a fair amount about the history of their movement, when they changed direction, when the plate got bigger, when the plate got smaller. I mean, this is just a snapshot of our time that we're all on the planet for this short amount of time. But if we go back in the past or even go to the future, we have different tectonic arrangements. Okay, that was the kind of broad kind of stuff. It's 6:16. We're drilling down now. And this will be hopefully fast-paced. What are the three types of convergent plate boundaries? Well, the answer is it depends on what type of crust is involved in the collision. So you see that word convergent, you should just think collision. Okay, all three of these, we're colliding the plates together. In slow motion, of course. This is 2 inches a year. It's a very gradual, slow, it's like a, sorry to be graphic now, it's like a head-on collision on the freeway. There's a drunk driver that went on the wrong ramp, and it's one of those. And it's a head-on collision. But it's in slow motion. It's 2 inches a year for both vehicles. And the impact of that head-on collision, you've seen the results of a head-on collision. The windshield is shattered, the headlights are shattered, the front engine block is pushed up into the passenger, that whole thing, right? And the backs of those two vehicles aren't even touched. It's just the front end of those two vehicles. Well, that's what we're talking about here. And the most classic case is taking two pieces of continental crust and colliding them together. Can you think of a mountain range on the planet today that is the result of two pieces of continental crust colliding? What's your answer? That's right, Kathy. The Himalayas. The Alps, correct. The Appalachians in days of yore, yes. Okay, so here's, obviously this is from last fall, so these are some notes that I was using. I don't have blackboards in our classroom. We have a brand new building, and I'm very grateful for it, but one of the casualties was we lost our blackboards. So I use this document camera that I have to draw on, and then it projects up onto the screens and the TVs and everything else. It's kind of satisfying, but it's just not like that old chalkboard. And by the way, have you noticed I didn't have room for my chalkboard, and I realized our last session I didn't even use the chalkboard. I haven't been using the chalkboard that much, so I'll probably go back to the chalkboard when we're outside, but inside I think I'm just doing this. And for some reason I can get better focus, I think, and better lighting. I can go real close here and I don't think I lose the focus. I'm not sure we had that outside. Okay, so we have our two continents colliding, and what I mainly want you to see is that we have some very significant kinds of rocks that form in this continent versus continent collision. And it's like a signature. Here are the rocks that are a signature of a convergent continent versus continent collision. And yes, I'm talking about the Himalayas and the Appalachians and the Alps, and there's some others as well, the Urals. Folded sedimentary rocks. Go a little deeper in the mountain range, plenty of metamorphic rocks. Go very deep in that mountain range, you'll find some granite. Folded sedimentary rocks, metamorphic rocks, granite in the core. But the most important message about these mountains is that these are not a volcanic mountain range. There's no volcanic eruption in the Himalayas. Have you ever thought about that? I mean, our guys that live here grew up next to the Cascades, and they know Mount Rainier and Mount St. Helens. They know that our mountains are volcanic. And without knowing much, they just assume that all mountains around the world are volcanoes, just because ours are. But depending on where you live, you know that most mountain ranges are not volcanic. So instead, we're just taking this originally flat-lying sediment. By the way, do you know what the kind of rock is on the top of Mount Everest, which is, of course, the highest point in the world? What kind of rock? What kind of bedrock the top of Mount Everest? It's limestone. And limestone or dolomite only forms below sea level. Warm, shallow sea with some corals and the whole thing, like a snorkeling place. And then that snorkeling rock gets lifted out of the water and before long finds itself whatever the elevation of Everest is. Amazing stuff. So this isn't going to happen overnight, but this is definitely the story with these convergent continent versus continent collisions. Now, of course, if we have that massive collision and an ongoing compression, we're going to have brittle deformation as well. We're going to actually crack the crust on a regular basis. So this is going back to one of our first live streams when I was out in the backyard with crappy stream quality, or maybe it was inside, I even forget. And you know that if I take these two blocks, these are not plates now, this is a smaller scale. I'm in a place within the Himalayan mountain belt. Maybe I'm in India, maybe I'm in China, maybe I'm in Mongolia, Nepal, wherever. Russia, Kazakhstan, Kyrgyzstan. There are routine regular earthquakes on reverse faults in a convergent continent versus continent collision. So not only do we kind of pile up all this crust to make a mountain range and get high temperatures in the core of it, that's why we have some granite. We don't have any magma coming to the surface, we don't have any volcanoes, but a real tragic side effect of this top picture are these regular magnitude 7 earthquakes that happen in Asia, often in villages with engineering practices where people are getting killed because of structures collapsing quite readily. So it's an ongoing thing. We all know this. This is happening every year, every decade. You read about these terrible tragedies, and it's a simple result of these two plates colliding. Well, which two plates are they? Have you figured that out? Which two plates are colliding to make the Himalayas? What are the names of the plates? The answers are the Eurasian plate and the, backwards again, the Eurasian plate and the Australian plate. And we're taking a curved surface of an earth and putting on a flat piece of paper, so it's not as satisfying as you'd like to have these two arrows coming head on. But essentially we have an Australian plate where Kathy lives. We have one tectonic plate that includes the continent of Australia, all this ocean crust of the Indian Ocean, and India. That's all on one block of lithosphere that's moving north. And as long as it continues to move north, we will continue to have tragic earthquakes in the Himalayan mountain belt. Okay, I'm moving on. I got a couple more, and then we'll turn it over to you, because I know that you'll have a lot of questions. So that was this. Now, what happens if we switch gears and have a collision? It's still a convergent plate boundary. The plates are still coming together. But what if we have essentially a mismatch? What if this is like a boxing match now. We got some lightweight against a heavyweight. If we have ocean crust colliding with a continent. For the first time, we have something called subduction. Subduction. Let me show you a beautiful poster of subduction. That was a week ago. It was Tuesday last week that I was in the high winds and my poster got ripped in half as I was trying to chase it down. And I've been using this ripped poster from Cindy Shaw since that time. Well, guess what arrived in the mail this morning? This arrived in the mail from Cindy Shaw's place of business. It's called Aurelia Press. And she has a website. And she was working with Patrick. Patrick and his mother contacted Cindy, and the three of them hatched a plan to send me 2 new posters. So thank you, Patrick. I want to show you my 2 new posters from Cindy. There they are. There's no rips on them at all. They're just, it's got that new car smell. This is right out of the factory. So viewers, if you want your own, Cindy says she has plenty. And she also sent me a CD with a bunch more stuff and wanted to thank me for passing the word about her wonderful work. So, my pleasure. So where are we? The middle picture, Oceanic versus Continental. Well, where can we go to see that? We don't have to leave my backyard. We don't have to leave the Pacific Northwest. We've already looked at this a fair amount. We do have an oceanic plate that's moving. It's called the Juan de Fuca plate. And it is subducting beneath the North American plate, creating all sorts of interesting stuff, including volcanoes. So we've already talked about this concept a fair amount. So let me just add a few things. We still must have reverse faults, and we do when we have a collision between plates. But we're leaving the top picture now, we're to the middle picture, and we can see not only do we have this ocean crust subducting beneath continental crust, we have a mountain range now that's actually erupting. And it's erupting regularly. Yes, that's Mount St. Helens, Mount Rainier, Mount Fuji, go around the world. Any situation where you have these beautiful stratovolcanoes, they are the result, oftentimes, of ocean plate that's subducting beneath the other. Okay, what are some basic rules? There's always an oceanic trench that marks where the subduction takes place. Next door to an oceanic trench, you always have an active volcano. Ocean crust is the one that always subducts. Continental crust never subducts. Why is this? There's two fundamental differences between oceanic crust and continental crust. First of all, ocean crust is very thin. Now we're talking about two tectonic plates colliding, but the crust that's riding on the top of those two tectonic plates has significant differences. Ocean crust very thin compared to continental crust, and there's also a density difference. And this is potentially confusing, so let me choose my words carefully now. If I take a fist-sized piece of the ocean floor and I take another fist-sized rock of the continents, in other words, I've got two rocks that are from two different crust types, ocean and continent. They got to be the same size rock. If I just have that, the ocean rock is going to be heavier. It's going to have a higher density because the minerals are different in an ocean rock versus a continental rock. The specific gravity of those minerals are higher in the ocean rock, therefore the ocean rock is heavier. It's more dense. Mass per unit volume. And that's an important point because if we have thin and dense rock colliding with thick and not dense rock, that helps explain to us why this ocean crust is begging to subduct compared to this styrofoam that we call continental crust. Continental crust never subducts. It's too thick and it's too buoyant compared to the ocean crust. And I chose my words carefully because quite often students raise their hand and say, well, shouldn't this be a lot heavier than this? It's so much thicker. And I'm like, well, yeah, but if we need to focus on mass per unit volume. Unit volume, the same sample from both settings. So, where do we go to find examples of this? The Cascades in the Pacific Northwest, the Andes of South America. Those are the two most famous examples, at least in our hemisphere. Then there's other places. You can go up to Alaska. The Aleutians have this, depending on where you are on the Aleutian chain, etc. Okay? Andesite lava coming from that situation. Let's finish out our... I'm sorry. Right. Before we finish out, I want to switch things up just slightly. I want to finish things. Where to go? I was reading my recliner before we turned on the live stream. This is the second day in a row now I'm touting this publication, and many of you did a nice thing and you looked up if these were available on Amazon, and apparently they are. A bunch of used copies for less than $10. So I strongly recommend, if you're really into this, reading these original papers. And I want to go back to this, The Trenches of the Pacific by Robert Fisher and Roger Revelle, November 1955. This is a full decade before plate tectonics becomes a thing. And these guys are describing these trenches that they have discovered and measured, and they have no idea why those trenches are there. But I think I showed you this quickly last time. They're showing, you know, this is in Scientific American. Imagine sitting and reading this at in your recliner with your pipe in, you know, December of 1955 and going, oh, that's kind of weird. And then looking at a map of this, going around the ring of the Pacific Ocean, and they're going to focus on the Tonga Trench right now. I'm going to read you a passage of this paper about the Tonga Trench, which is not the Mariana Trench, but very similar. Ready? It's story time. In April 28th, screwed up the first word. Blah. On April 28th, 1789, Lieutenant William Bligh, commanding HMS Bounty, had a memorable quarrel in the Pacific Ocean with his senior warrant officer, one Fletcher Christian, as a result of which they parted company and sailed off in opposite directions. Christian in the Bounty and Bligh in the ship's longboat. This historic mutiny took place near the great volcano of Tafua in the Friendly Islands, better known today as the Tonga Islands. Bligh and Christian were well acquainted with the fact that the oceanic topography around these islands was somewhat unusual, full of treacherous shoals and narrow inter-island passages. That was in 1789. Again, Robert and Roger are writing in 1955. But they could not know, for the methods of deep-sea sounding had not yet been invented, how unusual it really was, nor that this place would one day yield one of the most remarkable discoveries in the history of ocean-going exploration. Beneath the placid sea, east of the Tonga Islands, yawns a monster... I gotta say, this is my favorite sentence. Beneath the placid sea, east of the Tonga Islands, yawns a monstrous chasm nearly 7 miles deep. 100 years after the Bounty episode, another British vessel first plumbed its depth. I guess that would be in 1889. Surveying the ocean bottom around the islands, Pelham Aldridge, commanded the HMS Igeria, was surprised to find that on 2 occasions his sounding lead did not touch bottom until 24,000 feet of wire had been paid out. Aldrich's discovery prompted other nations to send out expeditions to explore the Tonga undersea abyss. Eventually, they traced out a great trench running from the Tonga Islands south to the Kermadec Islands. The deepest sounding made recently by the research vessel Horizon of the Scripps Institute of Oceanography is some 35,000 feet. The immense chasm plunges about 6,000 feet farther below sea level than Mount Everest rises above it. The Tonga Trench is now known to be but one member in a vast chain of deep, narrow trenches which, like the moats around the central basin of the Pacific, all of them parallel island archipelagos or mountain ranges on the coasts of continents. Along the coast of South America, the drop from the top of the Andes to the bottom of the offshore trench is more than 40,000 feet. And the length of the undersea troughs is no less remarkable than their depth. Some are 2,000 miles long. Remember, these guys had no clue that they were marking subduction and moving ocean plates. These great gashes in the seafloor are so unlike anything on land that they are difficult for us as land animals to visualize. It is hard to grasp the reality of a chasm so deep that 7 Grand Canyons could be piled on one another in it, and so long that it would extend from New York to Kansas City. Yet these are the dimensions of the Tonga Trench. I'm going to do one more paragraph. The size and particular shape of the Pacific trenches, muffler boy, stir our sense of wonder. What implacable forces could have caused such large-scale distortions of the seafloor? Why are they so narrow, so long, so deep? What has become of the displaced material? Are they young or old? And what is the significance of the fact that they lie along the Pacific Ring of Fire, in quotation marks? the zone of active volcanoes and violent earthquakes that encircles the vast ocean. So I don't know if those guys came up with Ring of Fire or if Ring of Fire goes back earlier than 1955, but again, that's something that resonates with pretty much everybody. And if it's unclear to you, the Ring of Fire is where all margins, almost all margins of the Pacific Ocean floor are subducting beneath all these continents that are closing in on this shrinking Pacific Ocean basin. And the result are these regular volcanoes around the ring. Let's finish our story and then we go to you. Thank you for your patience listening to that. Here's the last one, which is a little less, we're kind of finishing with a whimper. In an oceanic situation, we can have a completely submarine collision. And that's essentially what we're talking about with Tonga, I think. It's definitely what we're talking about with the Marianas Islands and the Marianas Trench nearby. So again, if you're an explorer, you're like, why do we have these islands all lined up out in the water? I don't get it. They're not random, there's like these lines. Well, we now know those lines, those islands are lined up because they're marking a submarine collision between two pieces of ocean crust. And what's the obvious question here? Well, if ocean crust always subducts beneath continents, why do we have this ocean plate subducting beneath this one? Why didn't this one go beneath that one? Why didn't they both subduct if they're both so thin and so dense? And the main answer is unsatisfying. It's due to local conditions. That's my best answer. You can have one plate moving faster than another. You can have, if you're looking down on two ocean plates, you can have kind of an oblique collision. In other words, it's not an east-west collision, but it's something like that. And so this plate coming in from the side is going to be more likely to go down. There's probably other factors as well. So there's not a good rule for that. And the students are like, I had that question. Why did one ocean plate subduct beneath the other? And I give that answer and they go, all right, whatever you say, bro. Or something like that. So we have volcanoes with two of the three types of convergent plate boundaries, but we definitely have mountains in all three pictures. We have mountains. We're making pretty much all the mountains of the world are the result of these three things, except for the Mid-Atlantic Ridge and those seafloor spreading centers. That's actually making a mountain from pulling the crust apart. That might be all I have for you. It's 6:40. I'll give you one more plug and then we'll go to you. This is the first textbook that I used when I came to Washington, and it's just called Geology. And the author is Stan Chernikov, who taught for many, many years at the University of Washington. And I visited with Stan a few times over the years. I don't know him very well. But he had, in his first edition especially, beautiful watercolors that to me were just works of art in illustrating a bunch of this. In other words, just aesthetically, it looked so different than many of the rest of the geology textbooks. Here's what we're talking about tomorrow, which is transform activity. So I'll come back to that tomorrow. Find something else here that he might have for us. Stan Chernikov, probably still available somehow. Okay, I purposely cut this short so that we would have a lot of time to go where you want to go. As always, I'll try to get the kids' questions, uppercase stuff, if you would. And let me get my laptop. Prop it right up here on the ladder, I think. I don't think I'm going to be worried about it flying off. Scrolling back. And let's go for it here. What formed the Rocky Mountains? Noticeably absent in our list, Bubba. Didn't talk about the Rockies. I'll just do it verbally. The Rockies are complicated. And the Rockies are complicated because it involves the exotic terrains that we were talking about more than once. So if you study all the basic geology of the Rocky Mountains, in other words, if you go to Wyoming or Colorado or Montana and you look carefully at all those, you bang on all those rocks, you make an inventory of those kinds of rocks, I would put the Rockies in our top picture. But the problem is, the Rockies don't exist on one of these black lines, right? Let's go to it. The Rockies, our biggest mountain range in North America, the Rockies are not on a black line. They're actually in here. So the main message is the Rockies are old. The Rockies are dead. Even though they're big, they used to be bigger. And when the Rockies were being built, there was a black line coming right through New Mexico, Wyoming, Colorado, Montana, Alberta, British Columbia. And actually, I think, yeah, these red notes are actually when I was discussing the Rockies in my class last fall, back when we could all be in the same room together and breathe the same air and I could touch students. Did I really say that? So the Rockies were active between 90 and 30 million years ago, and it was basically a continent versus continent collision between old North America and a bunch of those terrains coming in. That's a kind of a complete story for maybe another time. Thanks for the question. Bubba wanted that question answered. I'm seeing it every 5 lines. Hopefully you're satisfied, Bubba. Bubba Bong. Is that you, Bubba? Earl? I'm a given name's Earl. I go by Bubba. Did a bunch of... Is the Strait of Juan de Fuca being squeezed between the Olympics and Vancouver? Thanks for the question, William. I don't think so. I know you're visualizing the clockwise rotation, and it seems like we're closing that channel. But it's not. It's a good question. I don't know how to answer it easily, but maybe it is. I don't know how to answer it. The clockwise rotation is slowing down in there, and there's no other major tectonic forces. But technically, if we're talking about very slow motions, yeah, probably it is closing. Do you have any newer evidence of the Spokane, Australia connection of yore? No, what I shared is pretty much what I know, and I had to go through, that's from the Supercontinents live stream, if you're not familiar with what we're talking about. And that's a fresh lecture I just did last year at this time, so I kind of got as many new papers as I could get together, so I don't have more for you at the moment. There may be more that's been done, but I haven't seen it yet, and I'm on to other things. Does one type of plate boundary produce larger earthquakes than others? Absolutely. Again, from past live streams, I don't mean to be all clubby here. Like if you're the first time with us, I don't want to talk about stuff that you haven't seen. But earthquakes are part of the story anytime you're at a plate boundary. Earthquakes are a problem with all of these activities. All of them. Every one. I don't care what kind of plate boundary it is. Earthquakes are an issue. Potentially life or death issue. But if you subduct the ocean plate, then great earthquakes are possible. So the great earthquakes, the magnitude 8.5 or the magnitude 9 earthquakes, which have hundreds of times the energy relieved compared to a magnitude 7, those are only generated in subduction zones. So you want to avoid this if you're concerned about earthquakes. And as we saw, there's also regular, magnitude 7 earthquakes as well. But the big ones, the magnitude 9s, are only in those collision zones where we have ocean subduction. Thank you. Why are the plates the size they are? Were they bigger or smaller in the past? Absolutely. Let me give you an example. I'll do it with the So, too much glare, but we'll try, not too much glare. So we now have the ability to go back in time and reconstruct when plates were a different size, and even when plates were moving a different direction. For example, I'll use North America. You see this plate here that doesn't have a name on it, that's called the Nazca Plate. And the Nazca Plate is being created at these Pacific rise and it's being destroyed at the trench just off the west coast of South America. That plate used to be a lot bigger when South America was connected to Africa. So can you picture an ocean plate that was at least twice as wide? And so half of that's been destroyed because we keep encroaching this continent, which is not going to get destroyed, and we keep having that continent drift closer and closer to the thing that makes it. In the case of North America, we've already done that. We've already taken a huge ocean plate that used to be between these Pacific rise in North America, and it's totally gone. Because North America, we basically have been sprinting. It's a 100-meter sprint, us against South America, and we win. We crossed this finish line first. We're the champions. We're the champions. Stupid. Eventually, South America will cross this as well. So there's plenty of examples. Again, it's got to be the ocean crust. We're destroying ocean crust, we're creating ocean crust, and therefore we keep changing the sizes. We enlarge sizes, we decrease sizes. I can say the opposite for the Atlantic. The portions of the plates in the Atlantic Ocean are getting bigger each year because of this process we talked about at the Mid-Atlantic Ridge. Is the ocean crust more dense, heavier, because of the water weight? Has it been compressed? Thank you, Nick. The ocean crust is more dense just because of the mineral makeup. You can think of, I don't know, something in your kitchen. You make 2 loaves of bread and they've got different ingredients in them, and if there's heavier ingredients, this is kind of a dumb analogy, it's going to be a heavier loaf of bread. So I don't think the water has anything to do with it. And being compressed is definitely not from the weight of the water. I'm no physicist, but I don't think that's true. Why no volcanoes with continent-to-continent collisions? Mary, the 2 continents colliding don't create volcanoes? Never had that question before. We do generate the granite, which is magma, that's down there deep because of the high temperatures. I don't know if I have a good physical answer for you. Just in general, we have 3 main ways to make volcanoes on this planet. Divergent plate boundary, Mid-Atlantic Ridge, that's where the asthenosphere is coming up. Convergent plate boundaries where we subduct, and again we're generating deep melts. I think I have the answer now. Or the third way is a hot spot, and you have a deep mantle source. So I think the answer is we don't have a deep enough heat source with a continent versus continent collision. Never thought about it like that, but I think that's the way to go. Terry, I've explained reverse faults before. A reverse fault is when you have 2 blocks of crust and you squeeze the blocks and the hanging wall side, the block of crust that's above the fault, gets pushed up. The opposite is a normal fault where you have the 2 blocks of crust being pulled apart and you make an earthquake when the hanging wall goes down. That's called a normal fault. Did a bunch of geologists accept plate tectonics, or were there a J. Harlan Bretz type guy involved? Thank you, Robert. You can call Alfred Wegener a J. Harlan Bretz guy. That, if you were with us on Sunday morning, you can watch the replay, by the way, if you missed what we did last time. Brett spent most of his career with all this evidence, and everybody said he was crazy, but he didn't have the source of his water for the floods. Wegener spent 20 years finding all this data to convince people that the continents were connected together. Nobody believed him because he couldn't explain how it was possible to move continents. And it's not until we found the ocean floor data that came through. So he's the closest to a singular person. Otherwise, I don't have a great sense of what would I have done if I was teaching college geology in 1951, would I have been reading Scientific American and immediately using it in my classroom? Probably not, I guess. I think you kind of wait, as a teacher at least, to get a consensus. And as far as, I don't know of any major back and forth and, egos and other things. That might be part of the story, but I don't know about that part of the story in the 1950s and 60s. Good question, thank you. They're all good. Isn't there subduction in the Puerto Rico Trench in the Atlantic? Yeah, probably. The Caribbean plate is different than the North American plate, different than the Nazca and the Cocos plates, but I don't know the geometries down there very well. Are oil deposits beneath the Earth the lubrication for the tectonic plates to keep them from locking up and quaking? I think that the safe answer is no, Michael. Oil deposits are found at relatively shallow levels within tectonic plates. So I wouldn't think of them being at the edge or beneath tectonic plates because that's 100 kilometers down there. So the oil is definitely slippery and can be used as a lubricant, but those are, if we think of tectonic plates like, if you want to go back to a cake, the oil is just little puddles of oil in the frosting area where you didn't mix the frosting up very well and you still see little pieces of butter that didn't get melted or something. Evelyn, hello, are some plates more bossy, meaning they influence more than others? Oh, I like that, Evelyn. More bossy. You're a bossy plate. Interesting question. I've tried to help you see that the continental crust that rides on plates is indestructible, essentially, cannot be subducted, and therefore if you're the Eurasian plate and you're mostly continental crust, I suppose you are more bossy. Because when you have a Pacific plate or an African plate colliding with you, you're not phased too much. So maybe that's my answer, Evelyn. Did you want to say hi to these guys? You want to say hi? Come on, join these guys. Let's ask a few more questions. Let's see what they got. What formed crater of the moon? What formed crater of the moon? Relationship between the Chicxulub crater and what appears to be a Caribbean plate. Well, we now know that that crater in the Yucatan Peninsula is a place where there was an impact from a chunk of outer space and timed with the extinction of the dinosaurs and a major climate change, etc. John, if you're thinking that broke off the Caribbean plate away from something bigger, I don't see that. Can't rule it out, but I've never heard of that kind of instantaneous creating of a plate, if that's what you're getting at. Does water act as a lubricant? Well, you guys are into lubrication here tonight. We know the plates are moving. We have GPS receivers that show that from plate to plate. There is slippage past one plate past another, and earthquakes are the result. In the Divergent Plate Boundaries, we have all sorts of magma coming up, so if you want to think of that as a lubricant. But I'm a little confused by the allowing the plates to move thing, because we talked about last time that beneath the plates is this flowable asthenosphere. So it's, back in Wegener's time 100 years ago, everybody assumed that the entire Earth was rigid. Everything was like solid all the way through and not able to move. And we now realize the asthenosphere layer beneath the lithosphere, we now know that this layer is flowing like warm taffy. And so it's quite easy to move these plates around. Thanks for the question. I have been to New England. I know a little bit about the geology there, not much. I can say that for almost every place. I hardly know anything about any place except the Pacific Northwest. Do we have any idea how many plates have existed in the past? There's probably a dozen ocean plates that used to exist that no longer do at all. The Kula Plate, for instance, is an example that comes to mind. Again, I know mostly about the North American story. But we don't have any lost continental plates, because again, you can't get rid of that stuff. Is there dual subduction? Well, there are models. I don't know of any place today where you have, well, I think what you're saying, Craig, is you can have an ocean plate coming, let's say the continent is on the edge of your frame here, and I've got this ocean plate, let's say it's just one ocean plate, and then it starts to subduct, and then another piece of the ocean plate breaks off, and so we have like two trenches and two plate boundaries from a plate that used to be one. Is that kind of what you're getting at? I guess that is kind of the story in the other side of the Pacific, over with Marianas, etc. But I don't know if that's been backed up with evidence. Will North America run over the Hawaiian Islands or the hotspot? Yeah, I think we have to wait more than 100 million years for sure. But if we assume the trajectory of the North American plate continues, and that's just an assumption, it could change its direction, and assuming the Hawaiian hotspot is relatively stationary, sure. Can't wait for that. What do the plate boundaries look like? I love Apple products. I've never owned anything but an Apple computer. I just cannot get this fucking scrolling thing. Evelyn, age 7, do you think kids should have rock hammers? Also, will you do a live stream about geology tools? Thanks, I love you, from Patrick. Thank you, Patrick, I love you too. If your parents are comfortable with you having a rock hammer, and if your parents have safety glasses for you, and if your parents are at least observing you when you first try using a rock hammer a few times, I think that sounds like a great thing. And I don't have a lot of geology tools, but I'll think about making a program like that. Cause of the Smoky Mountains, question mark. The Smoky Mountains are part of the Appalachians, and the Appalachians were definitely the Appalachians, and therefore the Smokies, Dollywood, was definitely the result of two continents colliding to make that. And the Appalachian Mountains used to be very, very tall. The Appalachians used to look like the Himalayas. And you're like, well, why? And the answer is, long ago, 300 plus million years ago, North America and Africa collided. Tennessee collided with Morocco and made the Appalachian Mountains. Pretty cool, huh? What causes rift valleys? Well, let's picture Pangaea, for instance. Pangaea was a supercontinent. You're looking down on Pangaea now, okay? You're looking down from heaven on this supercontinent. And now we're going to start to break up the Appalachians. I was just talking about them. We're going to pull North America away from Africa, and it doesn't happen overnight. So there's probably millions of years where we just start to get my two pinkies to actually start to separate. And by doing that, we're actually forming a bunch of normal faults, and the crust is starting to fall down with a bunch of earthquakes. And then eventually we pull my pinkies apart enough where an ocean basin starts to grow in between. And that's what's happening today in Eastern Africa, the East Africa Rift. And an earlier form of that is happening in Nevada right now. If you're patient, Nevada will be at the bottom of an ocean at some point. Gavin, age 11, thank you for the question. Will an oceanic plate subducting below a continental plate eventually reach the core of the Earth? You know, Gavin, I used to say, I hardly ever say no, and that's like the end. But I used to say, well, almost for sure not, because when we subduct an ocean plate beneath another one, it eventually just replenishes the asthenosphere and it basically turns into warm taffy. However, I'm going to draw a picture for you. Oh! And you're like, boy, do we really need to take time to draw a picture? Yes, we do. This is the month of April. I had 4 downtown lectures scheduled, and I had spent a lot of time on those lectures. And I read a lot of papers on something called tomography. So Gavin's asking a tomography question, whether he knows it or not. So I don't want to use a Sharpie marker on a whiteboard. So there's been a lot of, here's an exciting new set of discoveries, at least in Western North America, and maybe around the world, I'm not sure. Gavin, here's the core of the Earth. That was a terrible circle, but I'm not going to redraw it. This is the mantle. And that's the crust. So just like an apple, the crust of the Earth is just the thickness of the crust of an apple. There's a lot of mantle and there is a core, just like a core in an apple. So what we're talking about tonight is one piece of ocean crust. I'm going to make them a lot bigger than they really are, just so you can see them. So we've been talking about collisions between pieces of apple skin. And in the case of ocean crust diving beneath a continent, like you're asking about, I was taught 30 years ago that the ocean floor would just kind of dive beneath the continent, talk about what we're doing tonight, but then it would just kind of dissolve. It would just kind of not melt, but it would change its temperature, and it would kind of go from cold taffy to warm taffy and just kind of blend in with the asthenosphere. Well, here's what we've been able to find using seismic waves and other indirect means. What do you think those are? Those are pieces of ocean floor that subducted, left the surface of the Earth, it left us, but they're still hanging down there. They didn't go away. There's these hanging slabs of ocean crust. And we can't go down there and get them and bring them back up. We can't even go down deep enough to drill to them. But by studying a bunch of waves of signals, basically, we've gotten signals from sending seismic waves through there that we can find those slabs. There's one of those slabs hanging right beneath Idaho, and that was the ocean floor that used to be offshore of Washington and Oregon. Thanks for the question. 7:06, we're going to do about 5 more questions. Are there any geologic processes that can't be explained with food? Sure. What makes the minerals different between continent and ocean plates? That's a tough one, Julie. I still think the conventional wisdom is the Earth was created, I'm choosing that word, the Earth was created 4.6 billion years ago, and many assume that the Earth was originally nothing but ocean crust. There were no continents. That's the, I think, conventional thought. And then as the hundreds of millions of years go by and we have lots of volcanic events and we separate out some minerals, we eventually develop continental crust. Pretty crappy way to think about it. Hard to back it up, but that's the word that's out there. So this process of volcanic activity, erosion, you eventually kind of create this continental crust with different minerals. But I don't know if I believe it. We're finally getting the hot sun underneath and coming in, but now that's too hot here. So I guess I'm happy with what we did. Are you of the opinion that areas like the Bermuda Triangle are due to geologic causes? There's a lot of this stuff, Jason, that I've never taken the time to try to read objectively. Bermuda Triangle, Atlantis, a lot of this stuff. The easy answer is no, there's no geologic connection, but I don't think you can just say that blanketly without reading carefully all the accounts. The problem is you have scientists who have the evidence for their myth or something, or story, but the problem is they usually want the story to be true, and now they're just trying to grab any kind of kernel of evidence, not all the evidence, but just one little piece of evidence and say, here you go, evidence. So it's tough to read those things objectively, in my humble opinion. Basin and range spreading related to overriding a spreading ridge? Generally, yes, David, and that's one thing I've learned from these live streams. Many of you are very interested in the concept of a continent drifting over a spreading ridge and what happens to the spreading ridge. I've always generally been interested in that, but I think I need to learn more about what we know and what we don't know about that, because a lot of you want more about that kind of overridden spreading ridge. What plate is north of the Pacific and Eurasian plates? North American plate actually collides with the Eurasian plate. I'm sorry, I'm backwards. Again, I'm working, you know, on my problem here, right? North American plate is colliding with the Eurasian plate. So there are some mountains up there that are continent versus continent, but in general, there is no plate up there. And you can kind of think of the plates moving very fast and very easily at the equators, but at the poles, you can kind of visualize log jams, where the plates are not moving very fast, and in cases they're kind of spinning, I think. I don't really know that, but I think that's true. So there's no major plate that's in the Arctic that's moving just as quickly or dramatically as the others. A few more. I just saw my picture and it's going like that. It's weird. Coin purse. Do I care to tackle the New Madrid Fault? I wish I had something intelligent to say. It's an old plate boundary where the Mississippi River drainage is today. It produced terrifying earthquakes in 1811 and 1812. As far as I know, we still don't know why those earthquakes happened. People have sent me some stuff on that, but I haven't taken the time to read it yet. Sorry. What's the future of East African rifting? What impacts will it have on the Indian Atlantic Ocean spreading? Thank you for the question, Santosh. I assume, without knowing the GPS data, that rifting in East Africa continues just as fast as it did when it started a few million years ago, and we'll have a new seafloor spreading center there. And I don't know, but possibly you'd create some new subduction zones on both margins of the Atlantic. But I don't know that area very well. I think I was way back, and now I'm going to scroll ahead to close our session here. Let me go all the way down to brand new fresh. How big was the Juan de Fuca plate? Do we know? Was there another plate too? The first live stream we did, Jason, was on St. Patrick's Day. And if you haven't seen that one yet, go back and watch that one. It talks about a Kula plate and a Farallon plate. And both of those plates are essentially gone. The Juan de Fuca plate is technically a remnant of that much larger Farallon plate. But the destruction of those two ocean plates has a big impact on what we have here in the Pacific Northwest. A lecture that I'm still excited to give, but it will have to wait till the fall. What causes movement on the South Sandwich Trench? I'm sorry, Sharon, I don't know anything about that. So Antarctica is stuck on the South Pole. I guess, Mike, but there is great evidence that Antarctica, if you go back far enough, was straddling the equator. And we have all sorts of plant fossils telling us that, separate from our global climate change data. Has there ever been a magnitude 9 quake at the Marianas Trench? Good question, Matt. I don't know, but I assume so. Anytime you have a major subduction zone, you're having a lock zone and then unlocking the lock zone every few hundred years. Now that I say that, I've never thought about that. Are magnitude 9 quakes only when you have an ocean plate subducting beneath a continent? Or have we ever had a great earthquake where it's ocean beneath ocean? I think the Sumatra quake in 2004 was ocean versus ocean. But I'm not sure we have any evidence of any great earthquake on the Marianas Trench to this point. What's the name on your plate poster? We'll finish with that. So one more time, and then we'll do a toast to you. One more time. This is, why isn't that focusing? Can you read that? Can I read it? Aurelia Press in Richland, Washington. And this was sent to Professor Nick. And the gal who makes this wonderful geology/art is Cynthia Shaw. And I think it just goes by the title of The Geologic History of the Pacific Northwest. Maybe you can read this. So, double-sided, wonderful for a wall, wonderful for a bunch of specific stuff that we've been talking about. I keep using it on purpose, not because I just wanted to help out Cindy, but because it's so damn useful. A toast for you. Hang on. Here's to your health. I hope you don't end up like this. Just kidding. This is the Iron Horse Brewery in Ellensburg, Washington. Former students from Central started the brewery probably 20 years ago. This is their trademark brew called Irish Death. It's about the only brand that I drink, but there's also a Cozy Sweater, which is a favorite Christmas time. So here's to you and your health. Here's to the health of your parents and your grandparents, your children and your grandchildren, all your friends, your neighbors, your pets. Thanks again to all the wonderful people out there who've been working through this difficult time. Here's to all of us. Thank you for joining us today. I think we'll be in the front porch again tomorrow because of rain and wind, and I'll have to memorize this sun position. Thank you very much. We'll see you tomorrow night. Love you. Good night. Thanks again, Patrick. Goodbye.